Hi, my name is Shahnawaz. In this lecture, we are going to introduce the subspace and product topology, and we'll start with the subspace topology. Well, let us first state a lemma. So we have this lemma which states that suppose xt be a topological space and if y is a subset of x, then the collection say t sub y, which consists of all subsets of x, open subsets of x, whose this ty has elements of this form u intersection y, where u is in t, u is open in x. Then we claim this is a topology on y. So this collection, so this is a topology on y. So we have a topological space xt, and we choose any subset y of x, and we take the collection of all open sets and take the intersection of each open set with y and make a new collection ty. Now we are going to prove this ty is actually a topological space on y. So to prove this topology on y, we have to prove the three axioms of being a topology. So the first axiom is that the empty set and the y itself are in t sub y. So since we know both the empty set and x are open, so since the empty set and x are both open, then so now these elements being in t, then their intersection with y are the elements of ty. Then empty set intersection with y, which is empty, is an element of t sub y, and x intersection with y, which is y itself, because y is a subset of x. So this is again in t sub y. So t sub y satisfies the first axiom, i.e. the empty set and the y itself are in t sub y. Now next we have to prove this t sub y is actually closed under arbitrary unions. So let us take a collection of elements of t sub y. So let v alpha, where alpha is in some index j, be a collection of elements in t sub y, but each element of t sub y is of this form, i.e. it is of the form u intersection y, where u is in t. So that means for these elements, for these v alphas, we have open sets in x, say u alphas, such that v alpha is u alpha intersection v alpha. So then there exists a collection of, say, the collection U alpha, where alpha is in the same index as J, of open sets in X such that this V alpha is U alpha intersection Y. Because this is the definition of this ty, because we chose this collection in ty, so each V alpha will be of this form, U alpha intersection Y. Now we have to prove this ty is closed under arbitrary union, i.e. we have to prove the union of all V alphas in ty. So then if we look at the union of these V alphas, where alpha is in index at J, so this is going to be equal union alpha in J, where V alpha is U alpha intersection Y. So now this is going to be equal, so we have like this, so we have U alpha, say U alpha 1 intersection Y union U alpha 2 intersection Y, and so on. So this is actually U alpha 1 union U alpha 2 union so on intersection Y. So we can take Y outside, so this is actually equal to union of alpha in J U alpha and it is intersection with Y. Now this T being a topology on X, so that means this T is closed under arbitrary unions. Now these U alphas being in T means this their union is in T, so this is an element of T. So since U alpha, while alpha is in J, is in T, so then this element over here, this is of the form an element of T intersection Y. So that means U alpha in J, V alpha is in T sub Y, by definition of T sub Y. So this means this collection over here is closed under arbitrary unions. Now let us prove it is closed under finite intersections. Finally, let say V1 V2 through Vn are in T sub Y, then so each Vi will be of the form Ui intersection Y, then there exist open sets U1 U2 through Un in X such that this Vi is Ui intersection with Y for all I runs from 1 2 through n. Now we have to prove this Ty is closed under finite intersection. So now let us take the intersection of these n elements. So let us take this intersection where this I runs from 1 to n. So this is actually intersection I runs from 1 to n. Now this Vi is of the form Ui union Y. Now we have this situation here, we have U1 intersection Y, then we have intersection here U2 intersection Y, so on intersection Un intersection Y. Now this is same as if we take the intersection of all Ui's and then take intersection y. So this is same as intersection of u i's where I goes from 1 to n, and it is intersection with y. Now note that these u i's, they are in t for all I where I is between 1 and n. So t being a topology on X, so t is closed under finite intersections. That means this element I goes from 1 to n, I mean the intersection of these ui's, so this is going to be an element of t. Now this being an element of t and y, so then we have an intersection with y, so this element over here, this is going to be in t sub y. So since I goes from 1 to n, ui is in t, we have, so this intersection over here, we have I goes from 1 to n, vi, so this is an element in t sub y. That means t sub y is closed under finite intersections. Hence this means t sub y is a topology on y, and this topology is called the subspace topology related to y. Now let us define. Now we know this is a topology, so now we are going to define the topology. So let xt be a topological space, and suppose y is a subset of x, then the collection t sub y which contain elements of the form u intersection y where u is in t is a topology on y and is called a subspace topology. On y, and in this case we call y a subspace of x, and we call y a subspace of x with respect to the topology t sub y. So for example, let us take R and suppose it is equipped with the usual topology tu. Now let us suppose, so let y be in this case an open set, say -1 1, which is a subset of x, then the topology y, and this is the subspace topology. So this is a subspace topology with respect y, where this ty consists the elements of the form u intersection y, which is -1 1, where u is in tu. Now we know that u being open in R with respect to usual topology, then u has to be of the form either an open interval or the union of open intervals. So this t sub y will be the collection of all open intervals which are contained in this -1 1. So this is the collection of all open intervals such that this AB is container in -1 1. So there is the possibility A is equal to B, because the empty set may be there, or we can take union the empty set, or we had to suppose we had to implement this condition that A is less or equal to Y, or we have to take phi, I mean the empty set, to be the element of this topology. Now it is natural to ask, if we have a topology with a given basis, say fancy B, and suppose we have a subspace topology, now we have to exhibit, I mean with respect to this fancy B, suppose this xt is our topology, and suppose this B is a basis for T, then if Y is a subset of X, then we have to exhibit, we have to look what the basis of the subspace topology with respect to this basis is going to look like. So for that we'll state the lemma. So let fancy B be a basis for the topological space, say xt. So if Y is a subset of X, then the collection say fancy B sub Y, which contain elements of the form B intersection Y, where Y is, sorry, this fancy B, this capital B is container in, sorry, is an element of fancy B. So we claim this is going to be a basis for subspace topology. So then the sub collection is a basis for the subspace topological space, I mean subspace topology T sub Y on Y. So let us prove this. So I mean we know this, if we take Y and take this collection T sub Y, then this is a topological space. So we are given, so this is what a topological space, which is called the subspace topology. Now we claim this fancy B sub Y is a basis for Y. That means we have to prove the two conditions for BY to be a basis for this topological space. So I mean we have to prove these two conditions. If we take any element Y in Y, we should be able to find a candidate, say B sub Y, such that Y is contained in B sub Y. I mean for each element in Y, we should be able to find a basis element in fancy B sub Y, for which contain the element Y. So let Y belongs to Y be any element. Since Y is also in X, because this capital Y is a subset of X, since y is also in X, we have, and we are given this fancy B to be the basis for X. So for this y in X, we should be able, I mean there is a basis element B in this fancy B which contain this element. So we have an element, say capital B in fancy B, such that y is contained in this capital B. Now this y being element of y and y being element of B means y is in the intersection of these two elements. Then y is in the intersection of these two elements, because this y is contained by both y and capital B. Now B intersection y is an element of this fancy by by definition, because by contains these elements. So what we proved for any y in y there is some element. So this is in fancy by. So for any y in y we are able to find an element in this fancy B sub y such that y is contained in this set. That means by satisfies first condition of being a basis. So for second condition, let us suppose this y is contained in the two basic elements of B fancy B sub y. So let y be an element of in the intersection of two basic elements, say B1 intersection y. Let us suppose, I mean we are going to take y to be in the two elements here. Now each element in this fancy B sub y is of this form. So let y be in this element and in the element B2 intersection y. We have to prove there is another basic element in B sub y which contain y and is contained in this intersection. So this is same as B1 intersection B2 intersection y. So that is y is in this intersection as well as in y. So that is y is in B1 intersection B2. Now note that B fancy B is a basis for X, and we are given this condition here: y is in the intersection of two basic elements of X. So there is some B3 such that y is in B3 and this B3 is contained in this intersection over here. So then B being a basis for X, there exists B3 in fancy B such that this y is in B3 and is contained in the B1 intersection B2. Now this means this y is in B3 and y is in y. Now y being an element of B3 and y being an element of capital Y means, so this implies y is in the intersection of B3 and y, since y is in B3. Now B3 intersection y is an element of this set over here, because I mean which is an element of B fancy B sub y. So what we proved, so hence for y to be in this intersection we were able to prove, so hence y is in B3 intersection y, which is contained in now this B3 is contained in the intersection of B1 and B2. Intersection now this is B3 is contained here and this intersection goes here, and this is y, but this is same as b1 intersection y intersection b2 intersection y. So if this y is in the two elements of b fancy b sub y, then there is some element in fancy b sub y such that y is contained here and this is contained in the intersection. So hence this fancy b serves as a basis for fancy b sub y. So hence this fancy b sub y is a basis for subspace topology T sub y on y. Now let us try to look what the open sets in subspace topology look like in the parent topology. So we have the another lemma. So let y be a subset of x. So if u is open in y and y is open in x, then this u is open in x. I mean, we have this space here, and y is a subset of x, and we have the subspace topology y T sub y, where the open elements in T sub y are going to be look like u intersection y, where u is in T. Now what we claim here, we claim the open set in the subspace topology is open in the parent topology only if the subset with respect to which we are taking the subspace topology is open in the parent topology. So let us prove this. So this is straightforward. So since this u is open in y, that is this u is going to be an element of the subspace topology, and hence this u will be of the form some open set in x intersection with y. So this is of the form v intersection y, where this v is open in x. Now if this y is in y is open in x, so if y is open in x, so then we have u to be the intersection of two open sets. That means u is open in x. So then u is the intersection of two open sets in x. Now since in xt finite intersection of open sets is open, so hence this intersection is open as well. So hence u is open in x as well. Now let us define the product topology. So we have the product topology. So suppose we are given two topological spaces, say xt and yt prime. So let xt and yt prime be two topological spaces. Then it is natural to ask, it is natural to define a topology on the Cartesian product of xy. So if we take the Cartesian product of x and y, which contain elements of the form x comma y, where this x is in x and y is in y. So we have topology on x, we have topology on y. Then it makes sense to define a topology on their Cartesian product. Now the topology which we are going to define on their Cartesian product is called the product topology. So let us define. So let xt and yt prime be two topological spaces. Now the product topology let us denote that by T sub p on the Cartesian product of x and y. See, so we claim this, I mean we define this topology on this set x as, so this is the topology which have the basis. So we are not going to exhibit the topology on TP, but we are going to define its basis, which have the basis like this. So this is fancy B. So it has all elements of the form u cross v, where u is open in x and v is open in y, i.e. u is in t and v is in t prime. So we call this B, so this B will generate a topology, and that topology is called the product topology on the Cartesian product of x and y. So any element of x cross y, I mean any topology, any element in TP is going to be the union of the element of subject B. I mean if we look at the collection of all possible unions of elements of objects B, that collection is going to be your TP, and this TP will be a topology on this x cross y, which is called the product topology. Now we are going to do more in the next lecture, I mean on product topology.